Hi everyone, it's Michael. So I have a remarkable problem for you all today. This one was posted on the Art of Problem Solving forum by Evan Chen. So he was a former IMO gold medalist for Taiwan. He's currently a grad student at MIT. He's written a book called Euclidean Geometry and Math Olympiads. And on top of all that, he has his own YouTube channel. So it's called V Enhance. And he has a lot of great problems that he goes over on it. So here's another great problem of his, and so if you'd like to try to solve it, feel free to pause the video. Alright, so I'm going to go over the solution. So we have a triangle ABC with in-center I. It's tangent to CA at E and AB at F. And then let G be the reflection of E across I, and H be the reflection of F across I. And let GH meet BC at point Q. And we want to show that IQ and IM are perpendicular, where M is the midpoint of BC. All right. So the first thing that I noticed is that it's not hard to see that FEHG has to be a rectangle. That's because, first of all, FI and H are collinear, because H is defined to be the reflection of F across I. So FH is a diameter. Similarly, EG is a diameter. And if we have any quadrilateral formed by the endpoints of two diameters, it's clear that that has to be a rectangle. All right, so I'm going to write this out. So FI and H are collinear, EI and G are collinear, and not only that, FI is equal to IH is equal to EI is equal to IG, and from there it's very easy to see that FEHG has to be a rectangle. All right, so where do we go from here? So we want to try to see, how do we use point Q? So Q is defined to be the intersection of GH with BC. So here's how I thought to do it. So we know angle IDQ is 90 degrees. So I'm going to label the midpoint of GH, which I'm going to call J. And then we'd also have IJQ as 90 degrees. So that means that IJDQ has to be a cyclic quadrilateral with diameter QI. So that's sort of my strategy to use point Q in the problem. All right, so I'm going to write this out. So we have angle IJQ is 90 degrees, and that's because the line from the segment from the joining the center of a circle to the midpoint of a chord is always perpendicular to that chord by symmetry. So angle IJQ is 90 and angle IDQ is 90. So IJDQ is cyclic and QI is a diameter. All right. So I just drew in the circle there. All right. So what do we want to show? We want to show that IQ is perpendicular to MI. But we know that QI is the diameter of this circle because these two angles are 90 degrees. So if MI were perpendicular to IQ, that would mean that MI would have to be tangent to the circle, since QI is the diameter. So then the question is, how do we show that MI is tangent to this circle? And one way to do it, which I'm going to try, is to show that angle MIJ is equal to angle JDI. That would prove that it's tangent. So that's my strategy here. All right, so how do I find angle JDI? Well, what I'm going to do is I'm going to extend DI to meet the incircle at a point and extend JI to meet EF at a point. So I'm going to label these 2 points. But basically, L is the reflection of D across I, and K is the reflection of J across I. And so angle JDI is equal to angle KLI. So I haven't said yet exactly why I did this, but it'll be clear in the next step, because I want to use the IM lemma in my video 65 to solve the problem. But first I'm going to talk about what I just mentioned. Okay, so it's clear that triangle IJD is congruent to triangle IKL. That's because K is a reflection of J across I and D is a reflection, and L is the reflection of V across I. So it's easy to see by side angle side that these two triangles are congruent. And so angle KLI is equal to angle JDI. And we want to show that angle JDI is equal to angle MIJ, because that would prove that MI is tangent to the circle. So we want to find angle MIJ, and so what I'm going to do here is I'm going to invoke the IM lemma. So if you haven't seen this, check out my video 65. But the IM lemma says that the line IM bisects AD. And I just hid the other circle. So I had shown earlier that IJDQ is cyclic. And I want to show that MI is tangent to it. But I'm going to hide the circle for a second because I don't want to make it look like I defined MI to be tangent to the circle. So I'm going to let MI intersect AD at a point N. And then by the IM lemma, check out my video 65 if you haven't seen this, AN is equal to ND. So a lot of Evan Chen's problems use the IM lemma. So I've noticed this, and so this will probably be the last one of them that I post in a while, just because I don't want it to get stale. But it's a very useful lemma that crops up all the time. Okay, so AN is equal to ND, and we also have LI is equal to ID. So I is the midpoint of LD, and N is the midpoint of AD, so AL has to be parallel to NI. So I'm going to write this out. So since LI is equal to ID, and AN is equal to ND, we have to have AL as parallel to NI. All right. And so we wanted to show that angle JDI was equal to angle MIJ, but angle MIJ, so that actually has to equal angle AIN. So I'm missing a segment in the figure, so I'm going to draw it in now. But clearly A, K, and I have to be collinear because K is the midpoint of EF, so that's true by symmetry. And so angle MIJ is equal to angle AIN, and then since AL is parallel to IN, angle AIN is equal to angle LAI. All right, so really we want to show that angle LAI is equal to angle KLI. So I'm going to say that again. Angle LAI we want to show is equal to angle KLI. And that's actually the same as showing that triangles KLI and LAI are similar because they both share one angle. So if they share another angle, that's the same as showing they're similar. And that is the same. With some work, you can show that's the same as showing that IK times IA is equal to IL squared. But IK times IA is equal to IE squared. That's true because IEA is a right triangle, and K is the foot of the altitude from E to AI. And whenever we have that situation, then we have that IK times IA is equal to IE squared. So I'm going to write this out. So here's a way of proving it in a way. So if we look at triangles IEK and IAE, they're both right triangles and they both share an angle. And so IEK has to be similar to triangle IAE because they're both right triangles that share an angle. And from there, it's not hard to show that IK times IA is equal to IE squared using ratios. So I'm not going to write out the full proof here, but if you haven't seen this, I'd recommend trying to prove it. And IE squared, well, IE is a radius of the circle, so that has to be the same as IL squared. Okay? And if IK times IA is equal to IL squared, it's not hard to show from that those two triangles are indeed similar. So I'm going to give a proof of that here. But basically, if IK times IA is equal to IL squared, that means IL has to be tangent to the circumcircle of AKL. So I'm going to write this out. But basically, if IL were tangent to AKL, then we'd have to have, by power of a point, we'd have to have IL squared is equal to IK times IA. And so by the converse of power of a point, we know that IL is tangent to the circumcircle of ALK. All right. And once we know that, then we know that angle ILK is equal to angle LAI. So I'm going to write this out. But now we're solving the last piece of the puzzle. So now it's all downhill from here because we have angle KLI is equal to angle IAL. And IAL, well, since AL is parallel to NI, IAL is equal to angle AIN, and angle AIN is equal to angle MIJ. So ultimately, we wanted to show angle MIJ is equal to angle JDI, but that's exactly what we've shown, because by transitivity, JDI is equal to KLI, and that's equal to angle MIJ. All right, so by transitivity, we have angle JDI is equal to angle MIJ, and that means that MI has to be tangent to the circle we drew before. So if we draw an IJDQ, then like we were trying to show before, since angle JDI is equal to angle MIJ, MI has to be tangent to that circle. So I'm going to draw it in again. But this angle condition means MI is tangent to that circle. And so since QI is the diameter of that circle, that means that MI has to be perpendicular to IQ. And that solves the problem. So since QI is the diameter of this circle, and MI is tangent to it, then IQ has to be perpendicular to IM. So I moved fairly fast in this, explaining this solution, but once you know that the key step is to use the IM lemma, a lot of it is sort of just angle chasing and doing calculations, which don't take a whole lot of cleverness. So I would say that the main clever step is using the IM lemma, and maybe also showing that AL is parallel to IM. And after that, it's not as hard. So if you like this video, give it a thumbs up. And if you'd like to see more like this, feel free to subscribe to my channel. Thanks, everyone.